An instrument probe climbs along a parabolic arc. At the very top, it explodes. Two pieces tumble apart, and one of them flies backward and lands exactly on the pad it launched from. The other sails onward and comes down somewhere far downrange. To find that landing point, you might expect to need the peak height, the launch angle, and the strength of gravity. You need none of them. A single idea, that gravity never noticed the explosion, collapses the whole problem. Here is the problem in full. An instrument carrying projectile of mass sub 1 is launched from a station on flat ground and accidentally explodes at the top of its trajectory. The horizontal distance from the launch point to the explosion is x sub I. The projectile breaks into exactly two pieces, and those pieces fly apart horizontally. The larger piece, m sub 3, has 3 times the mass of the smaller piece, m sub 2. To the surprise of the scientist in charge, the smaller piece returns to Earth at the launching station itself. Neglect air resistance and any effect of the Earth's curvature. The question we have to answer is how far from the original launching point the larger piece finally lands, a distance we will call x sub 3f. Start with the masses because that part is pure bookkeeping. Nothing leaves the system in an explosion, so m sub 2 plus m sub 3 equals m sub 1, and we are told m sub 3 equals 3m sub 2. Substitute the second into the first. 4m sub 2 equals m sub 1. So the smaller piece carries 1/4 of the original mass, and the larger piece carries 3/4. Now the key idea, take the system to be both future pieces together, and ask what forces act on it. During the explosion, the chemical forces are internal. Whatever push the smaller piece gives the larger one gives back an equal and opposite push. Internal forces cancel in pairs, so they contribute exactly nothing to the total force on the system. The only external force is gravity, pulling on the total mass. And we already know that the net external force equals the total mass times the acceleration of the center of mass. Divide out that mass, and the acceleration of the center of mass is simply g downward before the explosion, during it, and after it. The center of mass never learns that anything happened. It keeps gliding along the very same parabola the intact projectile would have flown. That fact helps only if we can catch the center of mass at a moment when we also know where both pieces are. Landing is that moment, but only if both pieces land at the same instant. They do, and here is why. At the top of the arc, the projectile's velocity is purely horizontal. The two pieces fly apart horizontally, so neither piece picks up any vertical velocity from the blast. Each therefore begins its fall from the same height with 0 vertical speed, so each takes the same time to reach the ground, and that time is exactly t sub 1, the time the projectile took to climb. Both pieces land together at time t sub f equals 2t sub 1. One more fact, the undisturbed parabola is symmetric about its peak. If the peak sits a horizontal distance x sub I downrange, the parabola returns to the ground at 2x sub I. So at the landing instant, the center of mass is at 2x sub I. Method 1. Put the origin at the launch station with the unit vector I hat pointing downrange along the ground. For two particles, the center of mass position is the mass-weighted average of the two positions. R sub cm equals the quantity m sub 2 times r vector sub 2 plus m sub 3 times r vector sub 3, all divided by m sub 2 plus m sub 3. Now evaluate every piece of that at the landing instant. The denominator is just m sub 1, since mass is conserved in the explosion. The smaller piece has come home to the origin, so r vector sub 2 is the 0 vector, which means the entire first term in the numerator vanishes. That single cancellation is why this root is so short. The larger piece sits at r vector sub 3 equals x sub 3 fi hat, which is exactly the unknown we want. And the left-hand side we established a moment ago, r sub cm equals 2x sub I hat. Put it all together. 2x sub I hat equals 3/4 m sub 1 times x sub 3 fi hat divided by m sub 1. The mass cancels completely. It never mattered what the projectile actually weighed. Strip the unit vector from both sides and we have 2x sub I equals 3/4 x sub 3f multiply both sides by 4/3. The larger piece lands at x sub 3f equals 8/3 x sub I. Read what that says. The big piece comes down 2 and 2/3 times as far out as the explosion point, which is 1 and 1/3 times the range the intact projectile would have had. And notice what never appeared anywhere in that solution: the peak height, the launch angle, the launch speed, and the gravitational acceleration g. None of them entered. Method 1 was short because it never looked inside the explosion. The second route does look inside, and to keep the bookkeeping honest, we name the moments we care about. At the initial state, time t sub 0 equals 0, the projectile leaves the pad. At state 1, time t sub 1, it is at the top of its flight, still whole, an instant before the blast. At state 2, an instant after the blast, it is 2 pieces. At stage 3, time t sub f equals 2t sub 1. Both pieces are on the ground. Conservation of momentum links state 1 to state 2. Kinematics carries state 2 through to state 3. Method 2. Let v sub 1 be the projectile's speed at the top of the arc. At the peak, the motion is entirely horizontal, so the velocity there is v sub 1 I hat. Horizontal velocity is constant throughout projectile motion, so the trip from the pad to the peak gives us x sub I equals v sub 1 times t sub 1. Hold on to that relation because it is what converts speeds into distances at the end. First, pin down the smaller piece. After the blast, it has to travel from the explosion point back to the launch station, a horizontal displacement of minus x sub I, and it has exactly t sub 1 in which to do it. Its horizontal velocity must therefore be minus x sub I divided by t sub 1. Substitute x sub I equals v sub 1 t sub 1, and the times cancel. The smaller piece leaves the explosion with velocity minus v sub 1. It exactly reverses the original velocity. That is not an assumption we made. It is forced on us by where the piece lands, now the momentum. Immediately before the explosion, at time t sub 1, the system is a single object, so the momentum of the system is m sub 1 v sub 1. Immediately after, the system momentum is m sub 2 times minus v sub 1 plus m sub 3 times v sub 3. Substituting the mass fractions, that is minus 1/4 m sub 1 v sub 1 plus 3/4 m sub 1 v sub 3. Because the explosion is instantaneous, the impulse gravity delivers during it, its force multiplied by a vanishing time interval is negligible. The momentum of the system is therefore constant across the blast. Along the horizontal direction, m sub 1 v sub 1 equals minus 1/4 m sub 1 v sub 1 plus 3/4 m sub 1 v sub 3. Every term carries a factor of m sub 1, so divide it out. Move the negative quarter across to the left. 5/4 v sub 1 equals 3/4 v sub 3. Multiply both sides by 4/3. The larger piece leaves the explosion at v sub 3 equals 5/3 v sub 1. It is moving faster than the intact projectile was, which is exactly what has to happen when the other fragment is thrown backwards. Finish with kinematics. The larger piece keeps that horizontal speed for the whole for time t sub 1. So its horizontal travel after the explosion is delta x sub 3 equals v sub 3 times t sub 1, which is 5/3 v sub 1 t sub 1, which is 5/3 x sub I. That is the distance beyond the explosion point, but the explosion point was already x sub I from the pad. So the two add x sub 3f equals x sub I plus 5/3 x sub I, which is 8/3 x sub I. The same answer reached down a completely different road. Two roads, one answer, 8/3 x sub I. The roads are not equally cheap. The center of mass route rested on three facts. Gravity is the sole external force, the parabola is symmetric, and both pieces land at the same instant. It never asked how fast anything was moving, and it never needed the actual mass, only the ratio of the pieces. The momentum route caused far more algebra, but it paid for that with information the first route simply cannot give, the actual velocities of the fragments. Had the question asked how fast the large piece was traveling when it struck, method 1 would have been useless, so the habit worth carrying away is this. Look first for a quantity the internal forces cannot touch. Explosions, collisions, and recoil are driven by internal forces, which can never change how the center of mass moves, and that alone is often the whole solution. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.